everyone. This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, we are going to discuss the problems related to the oscillator circuits. So in these problems, we are going to calculate the capacitances of the oscillator circuit as well as inductance of the circuit, and how much amount of series frequency and parallel frequency of the oscillator circuit, and how much amount of frequency is required to perform single oscillation from the oscillator circuit, and also the overall gain of the oscillator circuit. So these are the parameters we are going to calculate from the oscillator circuit. So here, before going to the problems in oscillators, what is the basic function of the oscillators here? So in the case of oscillator, it is used to generate the different types of waveforms that may be either a sinusoidal form or in the non-sinusoidal form. So these oscillators are one of the type of the feedback amplifiers, we can say. Why? Because in the case of oscillator, in order to design it, we are utilizing the amplifier circuit as well as the positive feedback network. So for the amplifier, if we add the positive feedback, so that it will become the oscillator circuit. And in the case of oscillator, we are not providing any external input signal. Only we will provide the supply for the oscillator circuit. By utilizing that supply, it will generate the different types of waveforms as the output here. Okay. That is the basic function of the oscillator here. By utilizing the positive feedback, we can able to design the oscillator circuit, and here we are not providing any input. And in order to design the oscillator circuit, here we require two conditions here. Almost the open loop gain of the feedback amplifier must be 1 here, and the second condition here, it is the phase angle provided from the circuit or feedback network is always 0 or 360 degrees here. So these are the very basic two conditions to design any kind of oscillator circuit. So these oscillators are available in different types. Those are utilized to generate different types of waveforms. Those are sinusoidal waveforms or non-sinusoidal waveforms. So in the case of sinusoidal waveforms, it will generate sinusoidal signal as well as cosinusoidal signal as the output. So the RC phase shift oscillators comes into the sinusoidal oscillators here. So the name itself indicating RC phase shift oscillators are designed with the resistors and capacitors here. The amplifier is common in any kind of oscillator circuit. The only difference is feedback network, how we are designing the feedback network. Depending upon that, it will generate the different waveforms. Suppose in the feedback networks, if we design with the resistors as well as the capacitors, those belongs to the RC phase shift oscillators. In that, we are having two types, RC oscillator as well as Wien bridge oscillator. But in both the cases, we are utilizing the resistors as well as the capacitors in order to generate the feedback network to provide the required phase shift as well as gain here. So that is in the case of sinusoidal oscillators. And while coming to the non-sinusoidal oscillators, so non-sinusoidal oscillators are used to generate the different non-sinusoidal signals, that may be the triangular wave or pulse wave or square wave, etc. Those kind of signals it will generate. The LC oscillators are coming to this type of category here. So LC type of oscillators, the feedback network is designed with the inductances as well as capacitances of the feedback network here. So that is the basic difference here. Depending upon the feedback network only, we will get the different type of waveform across the output of the oscillator here. And in order to solve the problems in the case of oscillator, we need to know the formula of frequency in different oscillators. So in our syllabus, we are having 3 different oscillators. One is Hartley oscillator, and one is Colpitt's oscillator, and one more is crystal oscillator here. So in these 3 types of oscillators, how much amount of frequency is required to provide the oscillations we are going to see now. So in this case of Hartley oscillator, we are going to utilize two inductors and one capacitor to design the feedback network. In the case of Colpitt's oscillator, we are going to utilize two capacitors and one inductor to design this. And in the case of crystal oscillator, we are going to utilize the crystal as the element in the case of feedback network to design such oscillator. So in the case of Hartley oscillator, the frequency of oscillation formula is 1 by 2 pi under root of LT into C, where LT is nothing but the total inductance. Why? Because we are having two inductances in the Hartley oscillator. So that's why the sum of two inductances we are taking here, L1 plus L2 plus 2M is nothing but the mutual inductance provided by the two inductors L1 and L2 here. So this is a formula in the case of Hartley oscillator to find the frequency of oscillation. And similarly, if we take the Colpitt's oscillator, in the case of Colpitt's oscillator, the formula is 1 by 2 pi under root of L C total here. In this case, L total. Why? Because we are having two inductors. But in the case of Colpitt's oscillator, C total. Why? Because we are having two capacitors in the case of Colpitt's oscillator. So the two capacitors are in series here. So that is C1, C2 by C1 plus C2 here. And next, in the case of crystal oscillator, we are going to calculate two frequencies here, that is series resonant frequency as well as parallel resonant frequency here. So to calculate the series frequency, the formula is Fs equal to 1 by 2 pi under root of L1 into C1. These two are the series elements. And to calculate the parallel resonant frequency, in that case we have to utilize 1 by 2 pi under root of L1 into C1 C2 by C1 plus C2 here. So these are the formulas required to to solve the problems in the case of oscillators. Yes, while coming to the problems, a Hartley oscillator is designed with two inductances L1 as well as L2 and a variable capacitance. So from this, we need to find the range of capacitance values if the frequency of oscillation is varied between 950 kHz to 2050 kHz. So we have already known in the case of Hartley oscillator, we are having two inductances as well as one capacitor here. So the two inductances values are L1 equal to 2 millihenries and L2 equal to 20 microhenries. And the capacitance value is we need to find. And this particular capacitance we need to calculate at maximum frequency as well as minimum frequency. Those are given in the problem. So at F equal to F maximum, the given frequency is 2050 kHz. And at F equal to F minimum, the given frequency is 950 kHz. At these two frequencies, we need to calculate the value of capacitance required to design such kind of Hartley oscillator. So in the case of Hartley oscillator, the frequency of oscillation formula is 1 by 2 pi under root of L total into capacitance. So here from this we have to calculate, to find this value we have to calculate first the total inductance, or where L total is equal to sum of L1 plus L2 here. So L1 value given it as 2 millihenries, 2 into 10 power minus 3, plus L2 value is given it as 2 microhenries. So if we solve this, we will get it as 0.00202 henries. This is the total inductance or equivalent inductance here it is. So now we need to calculate for F equal to F maximum equal to 2050 kilohertz at this particular range. To find the capacitance, I am taking the frequency 2050 equal to 1 by 2 pi under root of L equivalent value we have calculated 0.00202 into C value. So if we simplify this value, we will get the capacitance value as 2.98 picofarads. So at 2050 kilohertz, the capacitance required is 2.98 picofarads. And similarly, for F equal to F minimum, that is given it as 950 kilohertz. So at this particular frequency, the capacitance is 950 into 10 power 3 is equal to, here also 2050 into 10 power 3 1 divided by 2 pi under root of 0.00202 into capacitance. So if we solve this, we will get it as 13.89 picofarads. So at this 950 kilohertz, the required capacitance is 13.89 picofarads. So in this way, by using this frequency of oscillation formula of the Hartley oscillator, we can calculate the capacitance value as well as inductance value required to design that particular oscillator. So in this case, the capacitance value is varying from 2.98 picofarads to 13.89 picofarads whenever the frequency is changing from 950 kilohertz to 2050 kilohertz. So we're coming to the second problem. In a transistorized Hartley oscillator, so it is also a Hartley oscillator. Transistorized Hartley oscillator means the amplifier circuit in this Hartley oscillator is designed with a bipolar junction transistor. Here it is. We can also design this amplifier by using the FET as well as operational amplifiers. It is having two inductances, 2 millihenries and 20 millihenries, while the frequency is to be changed from 950 kilohertz to 2050 kilohertz. Calculate the range over which the capacitor is to be varied. So here the inductance values are changed here. So if the inductance values are changing means how much capacitance value is varying, we need to calculate here. So for that purpose, the given values are L1 is 2 millihenries and second inductance is 20 millihenries and the F minimum value is 950 kilohertz and F maximum value is 2050 kilohertz. So we need to calculate the capacitance at this frequency as well as at this particular frequency here. So again, by using the frequency of oscillation of Hartley oscillator, that is F equal to 2 pi under root of LT or L equivalent, we can write into capacitance. So now again we need to calculate first total inductance value is the sum of two inductances L1 and L2, that is 2 millihenries plus 20 millihenries. It is nothing but 22 millihenries here. The total inductance is. So now at F equal to F minimum, that is at 950 kilohertz, I am going to calculate the value of capacitance. So at F value 950, so I am taking here it as 950 into 10 power 3 is equal to 1 divided by 2 pi under root of total inductance is 22 millihenries into capacitance. So if we solve this, we will get the value of capacitance as 2.73 pico farads. So similarly, at F equal to F maximum, at maximum frequency, that is 1250 kilohertz. So at this particular frequency, if we calculate the capacitance, we will get it as 1250 kilohertz. That should be equal to the 1 by 2 pi under root of total inductance value is 22 into 10 power minus 3 into capacitance. So if we solve this, we will get the capacitance value as 13.79 picofarads. So in this particular case, whenever the frequency is changing from 950 kilohertz to 1250 kilohertz range, the capacitance is varying from 2.73 picofarads to 13.79 picofarads. So that's why it is indicated as a variable capacitance. The inductance values are fixed here, but the capacitance value is changing with respect to the frequency here. Yes. While coming to the next problem, this is related to the crystal oscillator. Why? Because in the problem itself they mention it as a crystal has the inductance value as 2 henries and the capacitance value as 0.01 picofarads, as well as the resistance value is 2 kilo ohms. And the mounting capacitance is 2 picofarads. So from this we need to calculate the series frequency as well as parallel frequency of the crystal oscillator. So from this we can say the crystal oscillator, in the case of crystal oscillator, the feedback network is designed with the RLC elements. In the case of Hartley oscillator, we are using 2 inductors and 1 capacitor. In the case of Colpitt's oscillator, we are using 2 capacitors and 1 inductor. But in this case, we are going to utilize all the 3 elements: resistor, capacitor, as well as inductor here. That is the difference between 3 oscillators. Okay, so here the given parameters I am writing here: inductance value is 2 henries and the capacitance value is 0.01 picofarads and the resistance value is 2 kilo ohms and the mounting capacitance Cm is 2 picofarads. From this we need to calculate series resonant frequency as well as the parallel resonant frequency. So here I'm going to calculate the series resonant frequency. Fs is equal to 2 pi under root of Lc here. So here the given values are 1 by 2 pi. Inductance is 2 millihenries and the capacitance value is 0.01 picofarads. 0.01 picofarads. So if we simplify it, we will get it as 1.125 megahertz. So the series resonant frequency is 1.125 megahertz here. And similarly, if we calculate the parallel resonant frequency, so to calculate the parallel resonant frequency, here we require 1 by 2 pi under root of L into C equivalent or C total here. So this value we can write it as 1 by 2 pi under root of L value is 2 millihenries and the equivalent capacitance is 9.95 into 10 power minus 15 here. Okay, so this equivalent capacitor we are taking from the capacitance as well as mounting capacitance here. So here the equivalent capacitor I am writing the C capacitance as well as the mounting capacitance divided by the sum of the 2 capacitances here. So the capacitance value is 0.01 picofarads and the mounting capacitance value is 2 henries. 2 picofarads, 2 into 10 power minus 12. So 0.01 into 10 power minus 12 plus 2 into 10 power minus 12. So the value of this one is 9.995 into 10 power minus 15. So this is the C equivalent resistance. So this particular C equivalent capacitance. So this particular capacitance only we are utilizing to find the parallel resonant frequency. So if we simplify it, we will get it as 1.128 megahertz. So if we see this, there is not much difference between the series resonant frequency as well as the parallel resonant frequency for the given crystal oscillator. Both are almost same here. Well, coming to the next problem, this is also related to the crystal oscillator. In that feedback, we are having RLC elements. So a crystal has the following constants. The given constants are inductance value is 50 millihenries and the capacitance C1 is given it as 0.02 picofarads and the resistance value is given it as 500 ohms and the C2 capacitance is given it as 12 picofarads. So here again we need to find the values of series resonant frequency as well as parallel resonant frequencies. If the external capacitance across the crystal changes from 5 picofarads to 6 picofarads, find the change in frequency of oscillation. So first thing, from the given parameters, we need to find the resonant frequency as well as parallel resonant frequency. And also in the second case, whenever the capacitance value is changing from 5 picofarads to 6 picofarads, how the frequency of oscillation is changing. That is nothing but at this particular frequency, how much frequency we are getting. At this particular capacitance, how much frequency we are getting, we need to calculate. So for that purpose, to find the series resonant frequency as well as the parallel resonant frequency, we require the C equivalent value first. So for that purpose, I am going to calculate the C equivalent value first, that is C1 into C2 by C1 plus C2, where C1, C2 are given in the problem. C1 value is 0.02 picofarads and C2 value is 12 picofarads. 0.02 into 10 power minus 12 plus 12 into 10 power minus 12 here. So if we simplify, we will get the equivalent value as 0.01996 picofarads. Okay, so then from this, I'm going to calculate the first bit, that is the series resonant frequency Fs, that is 1 by 2 pi under root of N C equivalent or C total. Sorry, C1 it is, C1 capacitance, that is 1 by 2 pi under root of inductance value is 50 millihenries. It is given 50 millihenries into the C1 capacitance is 0.02 picofarads. So if we simplify it, we will get it as the series resonant frequency 5.0329 megahertz. This is the series resonant frequency, and similarly we have to calculate the parallel resonant frequency by using 1 by 2 pi under root of L C equivalent we need to take here. To calculate the series resonant frequency C1 we need to consider. To calculate the parallel resonant frequency total capacitance we need to consider here. So here it is 1 by 2 pi under root of L value is 50 millihenries and the equivalent capacitance we got here it as 0.01996 picofarads. So if we simplify this one, we will get it as 5.0379 megahertz. So this is the parallel resonant frequency here. And next, we need to calculate the different frequency values whenever the capacitor is changing from one value to another value. So for that purpose, I'm letting the series capacitance 5 picofarads connected across the crystal. That is, actually in the crystal we are having one resistance, inductance as well as the capacitor. For this, again we are adding the one more capacitance RL. See, this capacitance is 5 picofarads we are connecting, and also the crystal capacitance Cx is present in the crystal oscillator. So this is only the feedback network of the crystal oscillator. We are not concentrating on the amplifier circuit. Why? Because we are going to calculate the frequency of oscillation of the feedback network only. So here from this is I'm taking here as C series or C2 capacitance, anything we can take. So to calculate this C2 value, that is C2 plus crystal capacitance Cx here. So the second capacitance value given it as 12 picofarads, and the Cx capacitance here it is 5 picofarads. So total it is 17 picofarads here. So then again, if we calculate C equivalent from this, we can write it as C1 C2 dash by C1 plus C2 dash. Instead of C2 capacitance, we are taking the sum of two capacitances C2 plus Cx. Why? Because we are connecting the one extra capacitance 5 picofarads across the crystal. So C1 value is 0.02 into 10 power minus 12, and C2 dash is 17 picofarads, and again it is 0.02 into 10 power minus 12 plus 17 into 10 power minus 12. So here, after simplification, this value is 0.019976 picofarads. That is the C equivalent value we have calculated. So by using this particular capacitance, how much amount of frequency we are going to get? So that we can calculate the parallel resonant frequency Fp dash, the new parallel resonant frequency. I am taking here it as Fp dash, that is 1 by 2 pi under root of L C equivalent dash. Instead of C equivalent, we are utilizing C equivalent dash here. So if we substitute all these values, that is 1 by 2 pi under root of, inductance value is 50 millihenries, and the C equivalent is 0.01997 into 10 power minus 12 here. So if we simplify it, we will get it as 5.035 megahertz as the new parallel resonant frequency. And the first capacitance 5 picofarads we have connected, and we have calculated the new parallel resonant frequency. And the second capacitance given in the problem is 6 picofarads. So when we connect the 6 picofarads across the crystal, how much amount of frequency of oscillation we are going to get here? So to calculate that, again we need to calculate the C equivalent with this particular Cx capacitance. That is C2 plus Cx here. That is 12 plus 6, 18 picofarads. And sorry, it is C2 dash. So C equivalent overall capacitance is now C1 C2 double dash by C1 plus C2 double dash. So this value, after substituting the C1 value given it as in the problem 0.02 picofarads, and C2 dash is 18 picofarads, 10 into 10 power minus 12, and again here it is 0.02 into 10 power minus 12 plus 18 into 10 power minus 12. So if we simplify it, we will get it as 0.01997 picofarads. C equivalent double dash. So with this new capacitance, we need to find the parallel resonant frequency, Fp double dash. That value is 1 by 2 pi under root of LC equivalent double dash. So 1 by 2 pi 50 into 10 power minus 3 into 0.0199 into 10 power minus 12. So if we solve this, we will get it as 164 Hertz. So in this way, the capacitance value is changing, means accordingly the frequency of oscillation is also changing here. The capacitance is increasing, means the frequency of oscillation value is decreasing here. Why? Because here this capacitance is inversely proportional to the frequency. Yes, while coming to the next problem, find the frequency of oscillations of a transistorized Colpitts oscillator. So here, this is the Colpitts oscillator, third type of oscillator, having C1 equal to 150 picofarads, C2 equal to 1.5 nanofarads, and the inductance is 50 microhenries. So here the given values are C1 150 picofarads, C2 is 1.5 nanofarads, and the inductance is 50 millihenries. So here we need to find the frequency of oscillation of this Colpitts oscillator. As we know that in the Colpitts oscillator, in the feedback network, we are having two capacitances and one inductance. So that's why they given it as two capacitance as well as one inductance value here. So to find the frequency of oscillation, the formula here it is 1 by 2 pi under root of L C equivalent value. Why? Because we are having two capacitances, so that's why C equivalent we are taking here. So to find this value, first of all, we need to calculate the C equivalent value. That is C1 into C2 by C1 plus C2 here. So C1 value is 150 picofarads and C2 value is 1.5 nanofarads, that is 10 power 9. So 150 into 10 power minus 12 plus 1.5 into 10 power minus 1. So if we simplify it, it is 136.36 picofarads. This is the C equivalent value. So from this, the frequency of oscillation is 1 by 2 pi under root of L C equivalent. So 1 by 2 pi, inductance value is 50 microhenries into 136.363 into 10 power minus 12. So after simplification, it is 1.927 megahertz. So this is the frequency of oscillation required to run the given Colpitts oscillator. Well, coming to the next problem, it is also a Colpitts oscillator. The given values, I'm writing plus the given values, the capacitance is 0.001 microfarads and the C2 capacitance given it as 0.01 microfarads and the inductance value is given it as 10 microhenries. In this, find the frequency of oscillation as well as feedback factor beta as well as voltage gain of the Colpitts oscillator. So again, to find the frequency of oscillation, first of all, we need to calculate the equivalent capacitance. So C equivalent capacitance is C1, C2 by C1 plus C2. That is 0.001 into 10 power minus 6 into 0.01 into 10 power minus 6. and again C1 is 0.001 10 power minus 6 plus 0.01 into 10 power minus 6. So if we simplify it, we will get it as 9.09 into 10 power minus 10 farads. This is C equivalent value. So now I am going to calculate the frequency of oscillation 1 by 2 pi under root of L C equivalent. That is 1 by 2 pi under root of the inductance value is 10 microhenries and the equivalent value is 9.09 into 10 power minus 10 here. So this value is 1.669 megahertz. This is the frequency of oscillation. This is the first bit. And next we need to calculate the voltage gain of the oscillator. I'm very sorry, gain of the oscillator, not voltage gain. Gain of the oscillator we can calculate by using the feedback elements, that is C2 capacitance by C1 capacitance, that is 0.01 into 10 power minus 6 by 0.001 10 power minus 6. So this value we will get it as 10 here. So the gain value we will get it as 10. And next, the parameter we need to calculate here, it is beta value. For oscillations, the condition is, A beta value must be 0. The two conditions I have already mentioned. The magnitude of open loop gain must be 1 and the phase angle of this gain must be 0 degrees or 360 degrees here. So from this condition I am writing A beta equal to 1. So where here beta is nothing but feedback factor. So beta equal to 1 by A, that is equal to 1 by 10 equal to 0.1. So feedback factor value is 0.1 required to run this particular Colpitt's oscillator. So we have calculated frequency of oscillation, gain as well as beta value. So while coming to the next problem, it is in a Colpitt's oscillator. The values of the inductors and capacitors in the tank circuit are. So the given values I am writing. The inductance is 40 millihenries. The capacitance, first capacitance is 100 picofarads and the second capacitance is 500 picofarads. So in this, first we need to calculate the frequency of oscillation, how much, and if the output voltage is 10 volts, if V0 is 10 volts, how much is feedback voltage. And next, find the minimum gain if the frequency is changed by changing L alone. Okay, how much amount of gain variation we are getting whenever the inductance value is varying. And whenever gain value is 10, how much amount of capacitance C1 is required. And also find the new frequency of oscillation with this new capacitance as well as with this new inductance. So FO new, how much we need to calculate. So first thing is, the first bit is we need to calculate frequency of oscillation. And again to find the frequency of oscillation, F0 1 by 2 pi under root of L into C equivalent, where C equivalent equal to C1 C2 by C1 plus C2. So if we substitute the C1 C2 values, we will get it as 83.33 into 10 power minus 12 farads as the C equivalent. So if I substitute that value here, 1 by 2 pi under root of inductance value given it as 40 millihenries. C equivalent is 83.33 into 10 power minus 12. So if we simplify this value, we will get it as 87.172 kilohertz. is the frequency of oscillation, that is the first bit we have calculated. And next, the second bit is what? If the output voltage is 10 volts, how much is the feedback voltage? So to calculate this value, we need to require the input voltage also here. So the input voltage, I'm very sorry, here we need to calculate the feedback voltage from output voltage. Okay. So in the case of oscillator, we are not providing any input voltage. So input voltage must be 0 here. So the feedback voltage Vf, which is the part of the output voltage only, that is nothing but some part or some portion of the output signal only, we are again giving back to the feedback network as the feedback voltage. Okay. So here the V0 value is given it as 10 volts. So for the Colpitt's oscillator, the gain value is C2 by C1 here. That is 500 picofarads by 100 picofarads. The value is 5 here. So the feedback voltage we can calculate by using the output voltage as well as gain here. Why? Because gain is equal to V0 by Vf here. So from this relation we can write Vf equal to V0 by gain here. So V0 value is 10 and the gain value is 5. So the feedback voltage is 2 volts here. So the Vf value is 2 volts whenever the output voltage is 10 volts. And next, minimum gain, the third bit given it as find the minimum gain if the frequency is changing by inductance alone. So in this case, to find the minimum gain, that is the ratio of two capacitances is 5, we have already calculated, but from the transistor HFE, minimum is equal to C2 by C1, that is also 5 here. So the gain value here, the minimum gain of the oscillator is equal to the minimum gain of the amplifier circuit only. And next, the fourth bit we need to calculate here, it is find the value of capacitance for a gain of 10 here. So whenever gain equal to 10, that value is C2 by C1, how much? Frequency here. So 10 equal to 500 picofarads by C1 here. Okay, so this C1 we will get it as 50 picofarads. Okay, and next the fifth bit we need to calculate here, it is find the new frequency of oscillation. So to find the new frequency of oscillation, we have to take the new capacitance value, that is C1 equal to 50 picofarads. C1 equal to 50 picofarads, just now we have calculated, and C2 we have calculated 500 picofarads. With these capacitance values, we need to calculate the new frequency of oscillation. So C equivalent value, by using these two capacitances, we will get it as 45.45 picofarads. Okay, so the new frequency of oscillation, FON, I am writing 1 by 2 pi under root of L C equivalent, that is 1 by 2 pi under root of L value is 40 millihenries and the equivalent capacitance is 45.45 into 10 power minus 12. So if we simplify it, it is 118.032 kilohertz. So this is the new frequency of oscillation whenever the capacitance value is changed. C1 capacitance value is changed to 50 picofarads. So in this way we need to find the parameters of the given oscillator. So in this session, we have discussed the problems related to the different oscillators. Those are Hartley oscillator, Colpitt's oscillator, and crystal oscillator. In that, we calculated the frequency of oscillations of all the oscillators and the feedback factor, gain values, as well as bandwidth values of the oscillator we have calculated. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.